Hello, hello, testing. Okay, everyone, I think we'll get started. It's 6 o'clock. So my name is Jing, in case you don't know me. I'm a fourth-year machine learning student here, and I'm going to be doing the recitation today. So we're going to start by giving you sort of like a review of linear algebra, trying to like brush you up so you have like all the tools to understand the class. You know, when Alex puts something on the board and it looks really obscure, you'll be able to know where it came from. So these are the topics I'm going to cover. We're going to go really kind of quickly through the first part, and then we're actually going to go through the full derivation of linear regression so you can see how like all these like tricks and stuff are used. And then we're going to do eigenvalues, eigenvectors, and the decompositions. And then hopefully I'll give you an example of like where you would actually use that stuff. And this is primarily for you guys, so if I'm going too quickly, then feel free to ask a question. And if you can't hear me, can you guys hear me? Then I'll try and speak louder. Okay. So we're going to start with something really, really simple. So I'm going to assume that everybody knows how to multiply matrices together. But I'm going to go over some of the properties. So it is associative, which means that if you multiply the matrices in a different order, you get the same result. It is distributive. Which allows you to do this. And in general, it is not commutative, which means that if you multiply two matrices in one order, that might not be equal to doing it this way. And that's because you could have a matrix that's n by m, and another matrix that's m by p, say. And yes. But if you do it the other way, so you're m by p, and then your n by m, you can't multiply these together. So the product does not exist. Okay. That's all I'm going to say about that. So what do you want to do with matrices? So can you see this? Okay. So we want to take the transpose of it is one thing we want to do. And so a transpose is just basically flipping the matrix. So if you have a matrix like 1, 2, 3, 4, the transpose of it is 1, 2, 3, 4. One thing that you should know is that when you take the transpose of a scalar, it's just itself. If you do this, you just get yourself back. And if you take a transpose of a product, then you need to reverse the order. And if you take a transpose of the sum, you can just distribute the transpose onto those matrices. Okay. So it's pretty basic. I'm sure you guys are already seen that. So one thing you might not have seen or worked with a lot is what's called the trace. And this comes up a lot, especially when you're doing derivatives. So for this, you need to have a square matrix, A. And basically what the trace is just the sum of the diagonal elements. So I'm going to do I equals 1 to n, AII. Another thing that is kind of neat is you can do the trace of a product. So these are all equal to each other. And it is equal to this expression here. And I'm going to unpack that for you, because when I first saw it, it didn't make sense to me either. So if you have a matrix, say A is equal to 1, 2, 3, 4. Sorry. And you have B, which is equal to 5, 6, 7, 8. So if we're going to multiply, so let me do A transpose. So we're going to do this guy here. So A transpose is 1, 2, 3, 4. So now we're going to multiply these two together. So A transpose B, 4, 5, 7, 6, 8. Okay, I guess you can't see that. Okay. And so when we multiply that together, we get, let's see if I can actually do this. 1 times 5 plus 3 times 7. 2 times 5 plus 4 times 7. 3 times 8. And 2 times 6 plus 4 times 8. Okay, so that's the product. Now if we want to take the trace of the product, we actually only want the diagonal elements. So that's this guy and this guy. But if you look at the original matrices, back here, 1 times 5 plus 3 times 7, that's that entry there. And then we're going to sum that with 2 times 6 and 4 times 8. So in a sense, it's just taking the kind of the element-wise products there. Does that make sense to everyone? Okay. Okay, so we're going to go over some properties of the trace. So if you have the trace of a matrix, that's equal to the trace of the matrix's transpose. If you're going to take the trace of a sum, that's equal to taking the trace of each one individually. So if you have a matrix where the product is square, like this, so say this is square, then the trace of the product this way is equal to the trace of the reverse. And this is called trace rotation. So it works if you have more than one. So if you have trace of A, B, C, you can keep rotating the matrices around. And these are all equivalent. And this is also very useful because sometimes you want to get them in a certain order to cancel some stuff out. Okay, so this is called trace rotation. Okay. So the other thing you might want to do with a matrix is you might want to take its norm. And actually, we're only going to go over vector norms right now, because those are the ones that are more useful. So a norm of the vector is the length of it, or the quote-unquote magnitude of it. And the most common is one that you probably know, which is the Euclidean norm, or the L2 norm. So the L2 norm looks like this. And where we've seen it, so I believe we've seen it already, is in ridge regression, where the objective looks like that. And another one which you'll become really familiar with if you stay in machine learning is the L1 norm. Sorry. And the L1 norm is just the sum of the absolute values of the vector. And so something that was like really hot in machine learning is L1 penalized regression, or like lasso. And that has the objective function that looks like this. And you guys will probably have to play with it for homework or so. So another one that you might not have seen before, but comes up a lot in optimization, is the L infinity norm. And that's equal to the max of all the elements. And these are all examples of LP norms which have a general expression. Okay. So one thing you'll hear a lot is the term rank, and people will say full rank, rank deficient. So what does that actually mean? So if you have a set of vectors, x1, x2 to xn, so these are said to be linearly independent if no vector can be represented as a linear combination of the remaining vectors. So the rank of a matrix is the size of the largest subset of the columns that are linearly independent sets. So if you have a matrix where A is in the space of reals m by n, the rank of A has to be less than or equal to the minimum of its rows and columns. Oops. And if the rank of A is equal to the minimum of mn, then you say that M is full rank. And what's amazing is often you hear that people say rank is the number of linearly independent columns, but the column rank is also equal to the row rank. So it can be like, you can use columns and rows interchangeably. So it's, I said that it was linear, that a set of vectors was linearly independent if no vector can be represented as a linear combination of the remaining vectors. But I would go with, like, this is the mathematical definition. It's probably more important than my description. Okay, so the next thing you want to do to a matrix is take its inverse. And so once again, you need a symmetric matrix here. Symmetric matrix and square matrix, and it has to be square too. And if you have those conditions, then if you take the inverse in any way like this, then you get the identity. So actually, on my first machine learning homework, when I did it, I didn't realize that if you had something like this, they had to be square matrices. So I had like rectangular matrices, and then I made them go to identity. So don't do that. Remember that they have to be square. So if the inverse exists, then we say that the matrix is non-singular. And otherwise, it's singular. So that's another term that people might refer to, and you sort of have heard about it, but you never knew like what exactly it meant. Okay, so we're going to go over some properties. So if you take the inverse of something and then you invert it again, then you just get the original thing back. If you have a product and you take the inverse, then this is going to look similar to the transpose. You have to reverse the order. And you might see the inverse transpose like written like that. So that's just equal to taking the inverse and then the transpose, or taking the transpose and then the inverse. And I'm going to write down this identity for you because it might become important. So if you have like a complicated matrix and we want to take the inverse of it, that's equal to this. And you're probably like, well, you just took a very like simple inverse and turned it into a way more complicated inverse. How does that make any sense? But while this looks more complicated, it is actually simpler to compute. And in some cases, it's faster to compute. Okay, so what is x? Yeah, so x is just a matrix, just like A and B. A matrix, yeah. So the whole thing, like A plus x, B, x, the whole thing has to be square. But x and b don't necessarily have to be square. Okay. Here? This? That's an inverse, sorry. By the way, I'll post my notes. Okay, so we're going to move on to orthogonal matrices. So really quickly, when we talk about vectors and we say that they're orthogonal, so if we have a vector u and v, then that means that their dot product equals 0. And we say a vector is, so this is, sorry. Okay, so this is an orthogonal vector. And then we also have this condition. So if someone says a vector is like normalized, that means its norm, and this is usually the 2 norm, or Euclidean norm, equals 1. So this is normalized. And if a vector has both properties, then we call it orthonormal. Now, the definition is different from a matrix. So if you have a square matrix, and it is orthogonal, that means that all its columns are orthogonal to each other, and are normalized. So in short, all of its columns are orthonormal. Mm-hmm. Why do you care about the rank of a matrix? So you mainly care about a rank of a matrix because it kind of represents how much actually information is there. So if you have a rank deficient matrix, that means that several columns of your matrix are actually correlated to each other. So one is like a scalar multiple of the other one, right? So off the top of my head, so this becomes important when you're doing feature selection, because when you're selecting features, you're essentially selecting columns of the matrix that are important for prediction, right? And so you want to select the columns that actually contain information. So you don't want to select like 3 columns that are multiples of each other. Does that make sense? Okay. Where was it? Okay, so if we have an orthogonal matrix, U, okay, you can see that. and we take its inverse. So that's equivalent to taking its transpose. So, and that means that this is true. And so this comes up when we do singular value decomposition later. Okay, so if u is not square, this is just a side note. If u is not square, but the columns are orthonormal. Columns are orthonormal. Then UTU equals identity, but this is not true. So when we talk about orthogonal matrices, we usually talk about the first case. Okay, so now I'm going to do an example, and we are going to derive linear regression from the very beginning. So I believe Alex did this in class, but he left out a lot of details. So I'm going to do this in gory detail. So for linear regression, we actually make a Gaussian assumption. So I'm going to write out the likelihood as the probability of the data given the parameters and this is equal to the product. This is the likelihood here. This is the likelihood. Okay, so this is a vector here. Okay, so in this expression here, y is a scalar and x is a vector. And if you kind of write that out, it equals this. And some of you, I guess, are taking stats this term, so you've probably seen this over and over. Okay, so this expression is called the likelihood. And normally what we want to do is we actually want to, instead of maximizing the likelihood, we actually want to minimize the negative log likelihood. Because this is kind of hard to deal with. So what we're going to do is we're going to take the negative log likelihood. And it's going to look like this. Okay, so here this is a matrix. This is a vector. And this is a vector. So we, yep. So the D is the data. Yep. Okay, so y is a vector. I can't like really do bold easily. Oh, let me just finish what I'm saying. So y is a vector, x is a matrix, and b is a vector. So a matrix times a vector will give you another vector, and this whole thing will be a vector. Yes?
Where did the Gaussian come from?
So linear regression is actually derived because you're assuming that the data came from a Gaussian distribution. Yes. Maybe. Does this do it? It's medium, audience lights low. Is that better? No? Is that better? Oh no, that's not. Is this okay? I have no idea how to do it, to be honest. Carlton, do you know how to do it? Do you know how to turn off these lights?
audience lights.
I feel like they're not on right now.
If those ones aren't on, it's the chalkboard light
Oh, okay.
that's on. I mean, if people could see that, that's fine.
Can you guys see the person who, yeah? Okay, we're good. Thank you very much. Okay. Okay. So is everyone with me so far? We haven't really done anything besides take the negative log of the likelihood. So what we're going to do now is, so this part, we're going to actually minimize it with respect to the parameter beta. So this part does not depend on beta. So we're actually just going to ignore it right now. So we're actually going to take this part. And this is called the residual sum of squares, or RSS. Or some people call it the least squares function. So when you maximize the likelihood, it's equivalent to minimizing the residual sum of squares. And this is also the same thing as finding the least squares solution, what we're doing here. So when you're trying to minimize an expression, normally what you do is you take the derivative. So we're actually going to expand it out to a form where it's easy to take the derivative of. So we're going to take this out. Transpose x beta. Oops. Oh, sorry. I was going to do it in gory detail. Okay, does everyone follow that? Yeah? Okay, so now we need to make this look a little better so that we can use our derivative tricks. So what I want is I want to get this first thing into the form of taking the derivative of something that looks like this. So the way we're going to do that is we're going to use the transpose tricks that we saw. So we're going to write this as x beta transpose y transpose. And then, so we're going to take this transpose in. So it's going to be beta transpose x transpose y all transposed. And then we're going to rotate them around, take the transpose in, y transpose x beta. And then for this part here, I'm going to make it look like x transpose y transpose beta. So now you can see this looks like A from over here. And then with this side's a little easier. We're just going to take the transpose in. And for here, we want it to look like equals A plus A transpose X. So if you notice here, this matrix now is square and symmetric. So that looks like that. So what we have, is beta.
Beta is
Okay.
a vector?
Yes, beta is a vector. So x is a matrix, beta is a vector, y is a vector.
When you take the derivative, why do you leave the transpose?
Sorry, I've not taken the derivative yet.
Oh, unless I use a partial. And you say that rule over there?
Yep. Mm-hmm.
Oh, okay. We can just get to it then.
Okay.
Well, because the transpose gets lost if you take a partial derivative, right?
Are you talking about the derivative of the square form? The x transpose a ax?
He's talking about on the left side where you transpose x with respect to x.
Okay, so is the question about the rule or the derivation that I've presented? Because I have not taken the derivative yet.
It's just the rule. So I guess that's just the rule.
Yeah.
When you take a derivative with transpose something. Okay.
Yeah, so there's not much I can say about like, so these are just like the matrix derivatives.
That's fine.
Matrix,
Yeah, sounds good.
okay. I mean, if we had like infinite time, I would try to prove them for you. Yep.
So x is a matrix of data, right?
Yes.
Is that in row form or column form?
So x would be, okay, so x is usually a matrix that looks like n by p. And it sort of depends, well actually, so if you're going to do linear regression, you need more samples than variables. So n is going to be greater than p. And then if you are going to do feature selection with like lasso or something, it could be possible that p would be greater than your n. Does that answer the question? N is the number of samples, p is the number of covariates or features.
The dimension of the data is so each sample is basically of p dimension, and you have n samples there.
Yes. Yeah, so every sample is going to be kind of a row here. Is everyone okay? All right. Sorry. Okay. So you can't see that. Okay, so we're going to take the derivative of this. Oh, sorry, I'm taking with respect to beta. Okay, so the first term is going to go away because it's not dependent on beta. The second term, thanks to our handy trick, you still see that. The second term is going to just be negative 2 x transpose y. And the third term is going to be x transpose x plus x transpose x transpose times beta. And so if you transpose this, and then you just get the same thing back, right? And so you get negative 2x transpose y plus 2 x transpose x beta. Are we good? Okay, so we've just taken the derivative of this expression with respect to beta. So if we want to actually minimize with respect to beta, we actually have to set the derivative to 0 and solve for it. So that's what we're going to do. And so it's actually quite easy to solve. These guys cancel, and you're left with beta equals x transpose x, negative 1, x transpose y. And these are called the normal equations. And Alex actually presented them as well, only he put them in like a different form. So this is like the vectorized form. And the way you solve this in MATLAB is you can implement it explicitly, but it's not very stable. So the way you would implement it in MATLAB is to just do beta equals x backslash y. And so this is like the derivation. You guys will probably have to do something like this on your homework in various shapes or forms. So if you have any questions about it, yep. So this is basically, it's basically solving the system that you have above, except it's using a QR decomposition in the background. So it's like more stable.
What is the x in the last word? What does backslash mean?
It means left divide. And then there's another one that is right divide in MATLAB.
So that left divide translates to x transpose and converting into x transpose?
I see what you're asking. There's
What does that x mean? Does it x backslash y just mean x into y inverse or something?
no. So honestly, like I've never given this like that much thought. I've always just learned this is how you solve the normal equations stably. Carlton, sorry, what? No. Yeah. Y equals x beta. No, it's not the same. Carlton. Do you know what they're asking? Yeah. Yeah. So yeah. So yes.
Do x transpose x left backslash x transpose y?
No, you don't. That's not what you do. So yes. So okay, let me just explain this again. So what you could do in MATLAB is you could do x transpose x, take the inverse of it with the inverse function, and then multiply it by x transpose y. And for certain matrices, that's fine. Sometimes but this is a better way of doing it. And what's going on in the background is a QR decomposition. And if you have normal equations in this form, then you can solve it this way. It's not meant to actually represent the exact equation like in math.
You do get the same answers though.
Yes, yeah. In fact, if you guys have laptops, you can try it right now and see if it works. Okay, so bonus question. I'm not going to do this, but this is something you can do at home to check your understanding. So I've basically just taken the derivative and set it equal to 0, but we still don't know whether this is a global minimum. Okay, and the way, so you can check this on your own at home as kind of like a practice. So what you need to do, it's really easy. You need to derive the second derivative. So I've just done the first, or it's also called the Hessian. And then you should find that the Hessian is actually positive definite. And if you know that the Hessian is positive definite, then you know that the function is convex. So the only stationary point you're going to get is actually the global min. So you can try that on your own. Okay. Any more questions before I move on? What's positive definite? I'm going to go over it right now. Good question. Okay, so you saw above that we have this form, x transpose A x, where A is square and x is a vector. Okay, so and the reason here, I'll first write it out for you guys. So you can write it out explicitly like the following. Okay. So this is really useful because you can define certain properties about A through this form. So one of them is positive definite. And the way you denote that is that A is greater than 0, or you can say A is squiggly greater than 0. And the set of all positive definite will denote with like a double S to the plus plus. And S just means the set of symmetric matrices. Okay, so yep, A is a matrix. So that means that the square form is actually greater than 0. So this is actually a number. And if you have, and in addition to positive definite, we have positive semi-definite. And so you denote that like this. And the same thing. So the square form is greater or equal to 0. And then there's also negative definite. And then negative semi-definite.
So is that for all x that has to apply? These conditions have to hold?
Um,
I assume that's the case, right? To be positive.
it can be like any x.
Right.
So yeah.
For a matrix to be positive definite, any x
Yeah.
has to meet this.
Yeah.
So usually when we do something is positive definite, when we do x transpose P Ax, we get a expression in x which is sort of x squared or something, and that's why it's always positive.
Yeah, then it's always positive definite. Yeah, so I'm going to go over an example like that. Okay, so there's one last one, which is negative semi-definite, and it's the same as negative definite, except there's a greater or equal sign. All right. So we're going to go over eigenvectors and eigenvalues now, and then there's one derivation that kind of goes back to what you were saying about positive definite. and how you prove it. Okay, so you guys see that? Okay, so once again, we have our square matrix. And we have lambda is an element of big C, and this C is the complex set, so not just real numbers anymore. So lambda is an element of C, and that's an eigenvalue. And X is an eigenvector if the following is true. So AX equals lambda X, and whereas lambda is a scalar, and X is not equal to 0. So we can rewrite this condition like this, where I is the identity matrix here. And so now, for a non-zero vector to satisfy this equation, that means that this thing here cannot be invertible, which means that it's singular and the determinant is 0. So I didn't cover determinants, I just assume you guys all know. So how would you find eigenvalues and eigenvectors? So theoretically, this is probably not the most numerically stable way to do it, but you can define the determinant, and the determinant will give you a polynomial in lambda. And then, so it'll give you a polynomial, and you can solve for the roots of that polynomial. And the roots will give you lambda 1 to lambda n. And then you'll have the eigenvalues. Once you have the eigenvalues, you can then solve this system of equations to find the eigenvectors. So why do we care? Oh, wait, first I have to tell you about properties before we can talk about why we care. Okay, so some properties. So one is, if you do the trace of a matrix, that's equal to the sum of its eigenvalues. The determinant is equal to the product. And the rank is equal to the number of non-zero eigenvalues of A. Okay, so there's another definition, and it's called diagonalizable. And so a square matrix is said to be diagonalizable if it's similar to a diagonal matrix. And a diagonal matrix, and what I mean about that is that A can be written as X. So I'm going to go over how we derive this. So we can write all the eigenvector equations simultaneously as this. So where the columns of X, so the columns of X are the eigenvectors of A. And so if the eigenvectors of A are linearly independent, then the matrix X will be invertible. So then we'll get A equals X lambda A minus. And this is what's called the eigenvalue decomposition of the matrix. And so remember, I just realized I wrote that wrong. Remember that if we have eigenvectors that are, if we have eigenvectors, they are orthonormal. So if we have an orthogonal matrix, then we can write its inverse as its transpose. So this is actually equal to x transpose. And we can actually write this like that in this form. So this here is a scalar. This is x is a vector. Xi are both vectors. And you guys have seen this before, right? So I believe that you have seen it in this form here, where you can wrap like a kernel feature around it. And this comes up all over the place. So it'll come up in SVMs later. Okay. Okay, so this is the derivation about the positive definite. So if you have a symmetric matrix, then all the eigenvalues are real, and all the eigenvectors are orthonormal. Okay, so that means you can write it like this. And we can actually write the orthogonal matrix as U. So A equals U lambda U transpose. And then what we can do is we can multiply it by x, which is just some vector. And then we're going to say here that y is equal to U transpose x. So this is just rewriting one vector as another vector. And because we're doing it this way, this can be rewritten as I equals 1 to the n lambda I yi squared. So, and this is like what you were saying, because this value here is always positive. So here, in order to determine whether the matrix is positive definite, you only have to look at the sign of the eigenvalues. Okay. Is everyone good? Yep. So the U's are just, I just use U because it's an orthogonal matrix.
Okay.
Yeah. It's the same thing.
In that last equation,
Mm-hmm.
if the lambdas have different signs, doesn't that also become the magnitude of the y?
So, right. So if they're both positive and negative eigenvalues, then it's an indefinite matrix. And I didn't.
Always. I mean, they could cancel, right?
With some. Eigenvalues. I'm not sure. You ask me after. Okay, singular value decomposition. Okay, we're almost done, actually. So in order to do an eigenvalue decomposition, you need a symmetric matrix. So, and in some cases, you want to decompose a matrix, and your matrix is not symmetric, actually, most of the time. So if we have any n by m matrix A, it can be actually decomposed in the following way. And it looks like this. So this can be, this is n by m. And u is n by n. And sigma is n by m. And this is m by m. B transpose A. Okay, so that's one way to decompose it. I still haven't learned, and it's almost the end of the lecture. Okay, so U are the eigenvectors of A transpose A. No. And sigma is actually the root of the eigenvalues. And V, the eigenvectors of A transpose A. And we're going to derive this part actually in a second. So one thing I wanted to let you know is there's the SVD, and then, so this you would do in MATLAB, SVD of A. You can also do something called econ SVD. So A econ. And that's a little bit different. It gives you, this is going to be n by m, I believe. And you get a square matrix here, which I think is m by m. And then V transpose m by m. So this affects kind of what properties hold for your, so I'm going to keep this up. So if you do just the SVD, then you will get that UU transpose is the identity, and U transpose U is also the identity. You'll get that VV transpose is the identity, and V transpose V is the identity. But for the econ version, for econ, UU transpose is not the identity. Okay, so how is this related to eigenvalue decomposition? So if you take A transpose A, or AA transpose, you can actually do the SVD decomposition. So you get U epsilon V transpose. And then on this side, you get V epsilon transpose U transpose. And so this cancels. This is identity. And then you end up getting V sigma squared V transpose. And on this side, you get the same thing. Okay, so, and this is how we get that the columns of V are the eigenvalues of A transpose A, and the columns of U are the eigenvalues of A transpose, and the actual sigmas that you get is actually the root of the eigenvalues. And so this happens when you have square matrices, that there's this relationship between SVD and the eigenvalue decomposition. Okay, so the last thing I'm going to go over is kind of an example of like where would we use something like SVD. So Oftentimes what happens, so this is topic is principal component analysis. So oftentimes what happens is we have like a high dimensional space, but we don't actually need to use those high dimensions. We can actually represent our data in a much lower dimensional space. So I'm going to do a simple example in 2D. So if we have x and y, and our data looks like this, well, you can say the data is occupying 2 dimensions, but in actuality, we could just like have 1 dimension here, and that would pretty much encapsulate like all of the variance of the data. So that's like the goal of like dimensionality reduction. And we can do this by using principal component analysis. And to do principal component analysis, you can use SVD. So if we take the SVD of a matrix A, we want to write A as sort of like a sum of simpler matrices. So we want to write A as the sum of simple component matrices, and P is the minimum of M, n, assuming that A. Okay. So now these component matrices are rank 1 outer products. So sigma I, ui, bi, t. So these guys here, this is a scalar. So this is from our SVD decomposition, the big sigma. And these two here are vectors. And so when we're doing this, we're actually doing the outer product. So it looks like that. And we know that these outer products are orthogonal to each other. So, okay. So their product is 0. Oh, sorry, this is j not equal to k. And we also know that the norm of the component matrix is actually just the corresponding singular value. Okay, so basically the singular values tell us the contribution that each component matrix is actually making to reproducing A. So if you, say, wanted to decide like where to cut it off, so how many component matrices do you actually need to represent your matrix, you can just plot the singular values. And so people do that, and I think it's called a scree plot. But they'll take, these are the principal components, and these are the singular values. And they'll plot it, and then you'll get something that maybe looks like that. And so you can decide you only want like the first 5 principal components, and that'll pretty much represent most of the variance of your data. So what time is it? We actually have the room for like 15 more minutes. So I'll show you, so these are the resources that I use. I will post my notes tonight, and I'll post them on my website first, and then I'll also email them to Alex and Jeff so they can post them on the general website. These are the resources that I use for the tutorial. So if you want to read more about any of the topics, I have links there. And so that's it for linear algebra. I have a few more notes going over some of the concepts that Alex talked about from class, just some optimization things. So if you want to stay, you're welcome to stay for 15 minutes. Otherwise, you can head out. Yeah.
Just going over the principal component analysis again.
Yep.
So what I understand is you could decompose. Can you just?
Sorry.
Yeah. So you I didn't quite get that jump. And the fact that B has to be minimum of m comma n means that you imply that A is a full rank matrix.
Okay, so
There are two things that like.
okay, so the number of singular values that you're going to have is the rank of the matrix.
So P is the rank, right, and not minimum of m comma n.
Okay, so let me think about this. Okay, yeah, so I think in this example, so I took this example from MATLAB. I think here they're assuming that the matrix is full rank, in which case P would be the minimum of M and N.
Okay.
So there are cases where you'll have a matrix that's not full rank. And in that case, like the singular values towards the end of your SVD are going to be 0. So the component matrix is going to be 0, in which case there's no point.
So and why are UI, DIT, and all of those orthogonal to each other?
Why are they orthonormal to each other? So I think that is the point of SVD, is to basically break up. So I didn't talk about like bases, but you know, like if you have data in your space, you have certain bases to your space, right? So, and like this, for example, so like each sort of like vector is kind of like a basis. So the point of SVD is to break it up into orthogonal bases, where you're sort of maximizing the variance of the data in each dimension. Does that make sense? A little bit? Come talk to me after. Okay, so Jeff basically gave me a list of things that Alex went over in class but didn't explain. So I'm supposed to like talk about them, and this is going to be really, really short. So I hope I don't get in trouble for saying that. This is all recorded. Okay, so the first thing that he talked about was, so he mentioned like the epigraph of a function. Okay, and basically what so like the formal definition of the epigraph of f is xt is an element of the reals where x is in the domain of f and f at x is less than t. But basically what you need to just know is if you have a function like this, kind of the area, the region above the function is called the epigraph of f. And f is only convex if the epigraph is a convex set. So this will become more important if you guys go on to take optimization. But so if Alex says it again, that's what the epigraph is. So another thing that he mentioned was the level set. So it's actually, to be more precise, it's an alpha sublevel set of a function. And this is the formal definition. So x is in the domain of f, and f at x is less than alpha. Alpha, it's an alpha. But again, if you just look at the picture, if you have sort of like a space and you have like a convex function, and you want to say like something about this particular level, and this is kind of like an alpha sublevel where f at x is less than a particular scalar value alpha. So those are level sets. So here there's people from ECE here. Delta function. So the delta function is equal to positive infinity when x equals 0, and 0 where x is not equal to 0. And it's also constrained to satisfy this equation. And basically what it is at 0 there's a spike, and everywhere else it's 0. It's a delta function. And the last thing is Cauchy-Schwarz. So Cauchy-Schwarz actually comes up quite a bit. And if you end up taking 10702, it comes up even more. So for any vectors u and v, so they have to be in R2 or R3. So the dot product of them is less than or equal to the norm. And I think he had this in one of his slides, so that's basically all it says. So that's all I have prepared. Do you guys have questions? Oh, someone asked about textbooks for the class and other resources. So when I took the course, I used Chris Bishop's book called Patterns of Recognition. But I didn't really like it. I also took it once when I was a master's student, and Kevin Murphy's book I liked better. So it's called Machine Learning with a Probabilistic Perspective. I know that Tom Mitchell has a book, but I don't think it covers everything that you'll need. And other than that, multiple professors have like their lecture slides on there. So like for example, Artie and Tom, like from previous courses, you can check out their websites, and they might have recommendations for books too. I will post these on my website, and hopefully in a couple days it'll be on the 10701 website. There's a link. If you just go to the website and click on my name, you can get there. Any other questions? So we're working on the homework right now. It will be available probably by the end of the week, and then you'll probably have 2 weeks. Thanks, guys. Come up here and ask me if you have more questions.
Can you give the references once again for today's recitation?
Yes. Can you actually give me 1 second? I need to turn off the camera.